Okay, good. So you see my screen, right? Do you see my screen? Say
Yes.
something. Okay, we have only how many people? We have only 9 people. Okay. So last week we started talking about the neural language modeling, neural networks, and we said that for a general classification setup we need the data, and for each data, let's say we have 4 samples, 4 sentences, and each sentence is like a um, input that we like to classify as positive or negative. Okay, so each sentence is xi and each output is yi is going to be true or false, positive or negative. Each sentence is going to be, what did we say last time, 3 word sentences, so each word has a 200 dimensional vector, and if we put them together it's going to be 600 dimensional vector each sentence, and we are going to assign a plus or minus to it. Okay, so yi are labels and xi are inputs. We talked about it last time. Okay, and here, if we are going to use the classical traditional machine learning statistical approach, we are going to use this softmax approach. Softmax can handle multi-class models. For example, it can handle, in our case, we are going to handle either positive or negative, right? Softmax can handle many classes, like 4, 5, 6, 7, 10, 1,000 classes, doesn't matter. But we are going to use it as a 2-class classifier. Softmax works this way. For any given input, I multiply that input with the weights of that class, okay, and also I multiply the input for all the weights of the corresponding class, and I make this division. Okay, so given x the sentence, what is the probability of this being positive, and I will also make sure that what is the probability of I will also prepare that the probability of being a negative or positive. Okay, so it will be, for our case, it will be for any sentence x positive plus p given x negative is going to be 1.0, because there are 2 classes. I think to make this more readable, maybe I should write positive and this one is negative. Okay, so softmax does that. So that means that with the softmax I have a vector for the positive cases and I have a vector for the negative cases. So these will be my parameters of this classifier. For this classifier to work, I need to find these parameters through training. I need to find the parameters through training. I didn't. Okay, good. So this is the classical softmax. This is the details. We talked about this last time. So how many vectors I am going to have in this classifier? I will have whatever the classes are. I mean, how many classes do I have? I will have, let's say, 10 classes. Then I will have my W is going to be okay. Each row is going to be 600 elements. So it's going to have 600 columns, and let's say I have 10 classes, I have 10 rows. W is going to be something like that. For the binary cases, I will have just 2 rows and 600 elements in each row. Okay, so with the softmax, if I like to do the training, this is what I am going to optimize. This is what I am going to minimize actually. Log probability of the total log probability minus log probability of the loss function. Okay, so for each case I will add these up and I will try to make it minimal. Remember, the log probability is good because we like to work with the additions instead of summation, instead of multiplications. It's going to be easy for computational purposes. Also, working with the additions is easier if you do it by the hand. Okay, good. And cross entropy, last time we talked about it. And this is the loss function that we are trying to minimize. Okay, why do we call the loss function loss function? Can anybody tell me why? Come on, people. It's a very simple question. Okay. Last time I started with the A's. Now I am gonna start from the middle. Okay. Furkan Kasım. Furkan, tell me, why do we call the loss function loss function? Furkan, are you there? So Furkan just logged in and he is not here anymore. Did anybody see Furkan? No. Okay. So I will take him out. Okay. Furkan Nehir. Furkan, tell me, why do we call loss function loss function?
Is it because it calculates the errors in our dataset?
Yeah, it calculates the error in our data set, and we like the loss to be, what is the best value for the loss?
0.
0, yeah. Because it is the error. I mean, we like our loss to be 0 so that we are at the very positive position, profitable position, okay? So for our training set, let's say I have 1,000 sentences and I run all of my 1,000 sentences through this loss function, and the total loss I like it to be 0. But unfortunately, due to noise or modeling errors or the other problems, my loss is never going to be 0. But I like to be very as small as possible. Okay, as small as possible. So for the loss function, that's for our case, we are going to use this. Remember, this is our softmax. Softmax is for use for predicting the class of a sample. Loss function is used for training. Okay, so these are two different things, and again, to calculate the prediction, maybe we can use our W as a matrix form and get the results for this one. So, okay, X is a vector. For our case, remember, let's look at this one. Since nobody seems to answering my questions, maybe I should try to wake you up a little bit. Let's go to the beginning. Okay. So this is what we are going to do. We said that our f function is w times x. W is a matrix. Okay. X is a 600 dimensional, x is a 600 dimensional input vector. If I multiply w by x, I am going to get a vector, right? So what is the size of f? What kind of mathematical structure is f? Is it a scalar? Is it a vector? Or is it a matrix? What is f?
How many classes did we have?
It is a number of
think-
classes. It is c, right? So
Yeah.
so f is a vector with c elements, right? F is a vector with c elements. Okay, that's what we say. So in fact, this one is, okay, this one is just the fy. Fy is you multiply the row number y with the input x, and this is fy. And if I do this calculation, then that means that I am normalizing all the f values so that their values add up to 1.0, so that I can use it as a probability. Okay, that's what we are doing with this f thing. Okay, good. But before doing this f thing, I need to calculate these w's. So with the traditional ML optimization, those w values, I have c number of columns of, or the rows of w, okay, and I put them one after other, and w, or my theta, is a c times d dimensional vector, single dimensional vector. Those are my parameters. Okay, what is the d? Is the size of the the input. C is the number of classes. So when we do the parameter optimization, when we try to find the theta values, the good theta values, the better theta values, this is what I am going to do. I will take the derivative of the loss function with respect to the parameters. So derivative of the loss function with respect to parameters, and that's where the stochastic gradient descent, the last time we learned, is going to reach. Okay, so last time we talked about this, we said that the softmax that we have learned, this one, is a very linear operation. You only do w times x, and we get f. Okay, so it's a very linear operation. Linear operation means that, let's say I have a two-dimensional axis, not 600 dimensional, but two-dimensional, so that it is visualizable. So this is x1 and this is x2, two-dimensional, this is 0. Okay, if I am going to classify the inputs, let's say this is input number 10. Okay, if I am going to classify this input number 10 as a true or positive, I need to put it somewhere on this plane, but this classifier can only classify this plane as a linear model. It would only say that, okay, I can draw this line, maybe some other line. Okay, I cannot do anything else. It has to be some kind of a line. Okay, so this is not enough for cases like this. Okay, for cases like this, let me erase what I have written before. Okay, linear stuff is not going to be good. Okay, softmax is not powerful enough. We need something better. Okay, we need something more powerful. So we are going to use, other than softmax, we are going to use a neural network for this. Okay, that's what we said last time. So a neural network is capable of, especially neural network with hidden layers, is capable of classifying my samples in this format. It doesn't have to be like a linear classification. In fact, I will start playing with that tool right now. Google has a nice neural network playground. Its name is Google Neural Network Playground. Let me open it up. Yeah, just make a note of it. Play with this one whenever you didn't understand anything about the neural networks. Neural Network Playground, and let me try to... Okay, so our case is like this. I have two inputs, input 1 and input 2, and my training data is like this. Okay, my training data is like this. In my training data, I have the positive cases and negative cases, and I like to find a classifier, a softmax classifier, okay, a softmax classifier that will nicely separate this two-dimensional space into two. And since I have two inputs, what am I going to do? So if I have two inputs, what would be the size of my W? Remember my W? Okay, what would be the size of my W if I have two inputs? I mean, the number of inputs is 2. So what I'm asking is
2.
Well, I mean, one side is 2, but what is C? Okay, for this problem, what is C and what is D? What are the numbers C and D?
C is 2.
Yeah, C is 2 because positive and negative 2. D is
1.
Not 1, because I have two-dimensional input vectors. I have C here, two-dimensional. I have two inputs, x1 and x2. Okay, so it is 2 times 2. So there are 4 parameters to optimize in this case. Okay, and I asked this tool to optimize it for me and show me the results. Okay, show me the results. And in this case, at the beginning, some of my values are 0.27 and minus 2, 0.42. They're just random numbers. Okay, I cannot see the other two numbers here because they're kind of hidden in there. And I asked the tool to optimize this thing. Let's make this sigmoid really. Okay, activation is like that. Okay, now run it, and after I started optimization, as you see, it finds those values, and my loss is, as you see, 0. It is very good, okay, because it perfectly divides this plane into 2, and everything up and everything down is correct. My loss is 0. It's very good. But if I increase noise, I added some noise. Okay, so my positives and negatives are not as clear as before. And if I run this again, it finds some kind of a boundary between them, but loss is not as big as small as before. It is 0.117. Okay, and let's see these numbers. Let me show you the training test data too. And this is my test data. See the difference? Test data and the training data. Okay, what is test loss and what is training loss? Can anybody tell me what is test loss and what is training loss?
We split the dataset, one for learning and getting the gradients, and one for validating or benchmarking our model, and tested that value.
So test data is never used in the training, right? Is that true?
Yes.
So how come our test loss is smaller than the training loss in this case?
chance.
It may be overfitted.
If you are overfitting, then your training loss would be very small and test loss would be large. This is underfitting, kind of. Okay, so suggest a way to make our test loss much larger than this. So to overfit, what would you do? What would you do to overfit?
Train more epochs.
Train more epochs, or maybe use less training data than the test data. So I am going to change the ratio of training to test data. The ratio of training to test data is going to be 10%. Okay, so let me show you the test data here. Test data is a lot more than the training data. Okay, and I'm going to run this again, and I am running it. As you see, the test loss is greater than the training loss. Okay, let's regenerate again. I regenerated. Again, the test loss is greater than the training loss. Okay, after a while, training loss, as you see, training loss is going down a little, getting it's a little bit better, but test loss is not changing. Let's wait until this epoch reaches 1. Is there any way? Okay, look at this picture. Do you think this is going to get better in terms of test data? What would you do to make this even better? How would you draw that line? It looks like that line is almost, because there is no way that I am going to get this blue dot out of there, because it has to stay in there. With a single line, I cannot do anything. Okay, so I don't think that our training loss is going to get any better. Remember what I said at the beginning, we like our loss to be 0, but most of the time it is not possible to get a loss of 0. Okay, so I think it's going to stay there. So test loss, let me show you the test data. Test data is like this. As you see, there are many blue dots and the yellow dots in the wrong side, because my test data is much more than the training data. Okay, just let's do the opposite. Let's do the opposite like that and run it again. Okay. Let me take this out and noise a little bit less and train it again. Maybe noise a little bit less. Train it again. Okay. So if this is the case, I can fit to my data. Again, but whatever I do, all I get is a single line in this world. I don't want that, because some cases are like this. For that one, I think last time we started talking about it. For that one, we started talking about neural networks. Okay, neural networks, and we are going to talk about it. This one is interesting. Last time I didn't talk about it. Okay, so we did not learn the word representations just to make this funny word vector comparisons. Okay, we are going to use those word representations for tasks like, okay, if this given sentence is a positive sentence or negative sentence. Remember my main task here. Okay, I am going to give I like MS positive, I excel is great positive. Remember sentiments, I am going to do the sentiment analysis of sentences. Okay, So the idea is this. If I use a softmax classifier to classify these sentences into two, I am fine. But what if I want to do this? Adjust your parameters of the softmax classifier plus the parameters of those vectors. I mean, what is the vector of I, that 200-dimensional vector? Change that 200-dimensional vector of I so that my training loss is smaller. Okay, that's the main thing that I like to do actually. So this slide says that. Okay, common in NLP deep learning, we learn both W and the word vectors. Okay, you start your word vectors with word2vec or glow or something else, fastx or something like that. Okay, then you use those vectors in a real application like the sentiment classification, and then during the training you both learn these W's and the word vectors, both of them at the same time. So your loss is your gradient descent that takes the gradient of this loss will work on all of your W parameters, also the parameters of all the vectors. So the optimization becomes something like that. Okay, so this is R to the power C times D. C number of classes, D is the vector size. V here is what is V?
Vocabulary.
It is the vocabulary size, right? Vocabulary size times D. It is so large, so very big optimization problem. So that's why we don't start this optimization problem from scratch. First, we find our initial word vectors, then we continue our problem with this optimization. And it works very well. So you will have vectors, word vectors specific to your sentiment analysis or the named entity recognition or the translation and etc. Okay, good. So this is a very good point. Don't forget about it. Last time I talked about it, I am not going to talk about it again. So the basic neural network unit is our logistic regression unit. Logistic regression unit, again, it takes an X as an input. It multiplies it with a vector of weights, and it adds a bias, okay, to that value. And I put this through this F function. F function, one typical F function is this. We call this sigmoid. Okay. The nice thing about this function is whatever you put as Z, it will map it between 0 and 1. I mean, even if Z is 0 or minus infinity or positive infinity, doesn't matter. Whatever you put, your results will be between 0 and 1. That's why some people call this logistic regression. Okay, binary logistic regression. So it's a regression thing. It produces a value, a continuous value, but the value is supposed to be between 0 and 1, logistic regression. So you could use this as a machine learning method too. I mean, all you need to learn is these W's, okay, these W's, and let's say I like to given a sentence, okay, I like to find it if it is positive or negative. Okay, that sentence has a 600-dimensional vector. Multiply that with 600-dimensional weight vector and add this number B, which is as a scalar, and put it through this function. It will produce a value between 0 and 1. If it is 0, then I will say it is false. It is not positive. It is 1. It is true. Then it is positive. Okay. And above everything this point 0.5 will be positive, and below it everything will be negative. Okay, so this is a nice binary classifier, right? Nice binary classifier. So I am not going to write the loss function for this, how to train it, because we have better than that. We have a better softmax classifier, and for that one we know the loss function. But anyway, I am not going to use this as a classifier by itself, but I am going to use it to go from this to that. Okay, to go from that to that. So logistic regression unit, don't forget about it. Okay, we are going to. So basically what you do is set of weights, okay, a vector, you multiply it with the input vector and you add a bias B. And W and B are the parameters of this logistic regression unit. Some people call this our artificial neurons. Okay, artificial neurons like this. Biological neurons, these are my biological neurons here. I have 4 of them in this picture. Okay, each one is a different color. Okay, and this is going to be my artificial neuron. An artificial neuron takes, okay, input of size n, multiplies it with dot product with a vector of size n, and adds a bias term and feeds it through this nonlinear sigmoid function. It doesn't have to do sigmoid, but for this case I will take it as sigmoid. And the nice thing is, if your inputs, you don't have to use a single neuron in your system, you may have more than one. So this is my first neuron, second neuron, and third neuron. Okay, and each one is each one has its own set of weights. Okay, if my input is of size n, this one will have a vector of size n, second one will have a vector of size n, and third one will have a vector of size n plus the biases. Okay, and so what can I do with this? I can feed all of them to a softmax, okay, and produce the class scores for each score, or I could add this to another neuron like this. Okay, so one layer and second layer, it goes like that. The nice thing about this one is, at the end of this network, I will add, okay, I will add nonlinearity to my classification capabilities. So the result of this classifier, okay, is not a linear classifier anymore. I can represent nonlinear decisions with this kind of approach. Okay, I can represent nonlinear decision with this kind of approach. Okay, good. So let me show you the same idea with this Google's neural network playground. Let me add, okay, three neurons to my immediate layer. Okay, and I ask this data set to be trained with this network. I could have done this with a original machine learning case, but I like to do this with this. Okay, I run this and linearly it separates very nice. It's fine. But what if my data is like that? Okay, my data is, can you separate this into, can you classify this? using just a linear relationship. Let me try to do that. Okay, it is trying to do something. Okay, let me start from the beginning. No, it goes there. Let me regenerate my data, other type of data, and do this. Whatever you do, I can separate this, I can divide this, classify this space into two using a line. As you see, my training loss is 0.5. Why is my training loss is 0.5? I cannot get better than that. Can you tell me why my training loss is around 0.5? Whatever I do, it is around 0.5. Regenerate 0.5. Always. I add noise, maybe more noise, and run it 0.5. Can somebody tell me why I keep hitting this 0.0 loss? Remember, I like my loss to be 0, but it is always becoming 0.5.
Because this space can be divided into two with only linear line.
Yeah.
So more complex line to get a better loss with 0.
Yeah, exactly. Look at this map. Okay. Whatever line you draw, on one side of the line will be half blue, half yellow or orange dots, right? Doesn't matter. Whatever you do, okay, one side is going to have, look at this side. Half of them are blue, half of them are yellow. I cannot get better than that. Okay? So a line is not going to cut it. Line is not going to cut it. I should do something better. That's why I am saying that I am going to more neurons between the input and the output. Let's optimize this now. Okay, I am doing something like that. Okay, is this? Yeah. So this is getting better and better and better. As you see, my boundary is not a line anymore. It is something like that, and my training loss is 0.14. Test loss is something like that too. So it is doing very good. It's much better than 0.5. And if I do this more fair, noise is less noise, and regenerate, let's optimize this. Okay. It should get better than that. And training loss is getting smaller and smaller and smaller. Only these parts are not being taken care of. And there is a hope that it will recover that one too. Let's wait. Let's wait until we reach 1.0 epoch. What is epoch 1.0?
We have gone through all of the data sets.
We have went through all the data set. Yeah. Selman, do you know how many lives are you saving? Okay, so I think I will put a quote on you. Okay. It might get better or may not be that better. No, it didn't. I don't think that it will get better. Training loss is very small, and test loss is small too. So this is yeah. This is basically it's going to state that it's not going to recover those. It could have done better than that, but maybe we should add more linearity. That's what we are doing with this addition of these extra layers.
So if we change the activations to non-linear to linear in the hidden layers, would it act like a linear?
Yeah,
totally
exactly.
linear
Yeah,
function?
I mean, if we if we FC, remember this, if FC instead of using this, let's use Z times, let's say, K1, a linear relationship. If I have a linear relation like that, okay, non-linear relationship, then in that case, we will not have this non-linearities. I think there is this activation linear like that, okay? Doesn't matter how many you add in between them. Whatever you do is going to be, doesn't matter. Let's add more neurons and let's add more layers. I am adding more layers. Okay, run it. It's going to be a line all the time. It cannot represent a nonlinear relationship between the inputs. It always have to be linear. So that's why it is important to have this function as a nonlinear function. Okay, in this case, what we are using is sigmoid, and we like sigmoid because sigmoid fits everything between 0 and 1. It is differentiable, and it's going to help us. It's going to help us with the differentiation stuff. Okay, and we like to take the derivative of e to the power x because the derivative of e to the power x is e to the power x. It's the same thing. Okay. Good. Let's move on a little bit. As I said before, if you add more layers between input and output, you will have a multi-layer neural network. And deep learning means that deep learning models are the neural network models that have many layers, more than 10, 12. Okay? If you have more than 10, 12 layers in your neural network, that's called a deep learning model. Nowadays, 150 layer networks are kind of the most popular ones. You can go up to 1,000 layers, no problem, but currently we don't get better results than 150 layers. Okay, so let's look at this layer. Okay, we call this a layer now. Remember, each of these is a sigmoid activation, and each of these has a weight vector. Okay, each of them is a weight vector. Okay, let's look at this layer now between them. Okay, so A11 does that. Okay, it takes X1 as input, it multiplies it with W11. Okay, then it takes X2 and it multiplies it 1, 2, W12, and this, and then the bias. Okay, and A2 this does the same thing but with its own weight set. So if you look at this picture, if you put all the A's one after the other like a matrix, you end up with this W. Okay, W is a matrix. Each row of W is the weight vector of A1, A2, A3. And of course, I have this bias vector, and I add them at the end. And I put them into this function f. But as you remember, that function f is a scalar function. It takes a scalar and produces a scalar. So what we do is, okay, the output of this A1 is our, okay, Z1. The output of A2 is Z2, Z3. So I will take, okay, or maybe I should say it this way. No. Let me call it whatever the book says, okay? Let me say this is FZ1, and Z1 is this. And this is FZ2. So this F works like this F works like it has a number of inputs and it runs this sigmoid function on those number of inputs and it produces a vector. Okay, it produces a vector. Okay, so this Z is now a vector. It takes a vector and it produces a vector. A is a vector. What is the size of the, okay, what is the size of this vector Z? Selman, you don't say it. Somebody else is going to say it, okay? What is the size of Z? Here. What is the size of Z? Z is a vector, right? And a hint for you, the size of Z is the same as size of A, and both of them are one-dimensional vectors. What is size of Z?
Is it 4?
Well, no. Well, okay, what do you mean by 4? What do you mean by 4?
Is a vector, not a matrix.
Yeah, but where did you get that number 4?
With axis and plus bias.
So you are saying that the size of Z is the number of inputs. Is that what you are saying?
Input plus 1, yes.
Well, I mean, by coincidence, it is the same thing, but no, it is not the size of the input. Remember, for each Z is for each neuron, right? Each Z is for each neuron. So size of Z is the number of neurons in the first layer. Okay? Size of Z is the number of neurons in the first layer. So whatever, okay, in this case, since the number of inputs is the same as the number of neurons here, in this case, but by coincidence, but see here, Z1, Z2, Z3, Z1 is A1, Z2 is A3, Z2 is A2, and Z3 is A3. It goes like that. Okay? Good. And I think we talked about this nonlinearities. I mean, f has to be a nonlinear function. If it's a linear function, then using more than one layer doesn't make any good for us. Okay, so that's kind of a basic introduction to neural networks. Let's go back to natural language processing. Okay, let's try to look at this named entity recognition problem, and let's try to solve this problem using neural networks. Named entity recognition is this: you are given a paragraph, a text, natural language text, like this one. Okay, your job is to find and classify names in the text. The text is this: the European Commission said on Thursday it disagreed with German advice. Okay, so I am going to find the names. European Commission is a name and it's organization. Okay, I find the name and I said that it's an organization. Said on Thursday it disagreed with German. German is, again, name. Its type is miscellaneous. Okay, and France is a name, location. Britain is a name, location. Okay, Fischler is a name, but it's a person. Again, it goes like that. Welsh National Farmers Union is organization. Okay, name and organization. John Lloyd Jones is a person. BBC is an organization. So this is called named entity recognition. Find and classifies names in text. This is a very useful NLP application. Okay, especially for the question answering systems. Usually, if you have a question about this paragraph, the answer is one of the names. Okay, for example, the question, who did not agree with German advice? Okay, this is the question, right? So you would come here and your results, Okay, I'm going to use this one. You will say European Union. Okay. On what radio the chairman talked, gave an interview? You will say BBC. Okay. Who backed Fischler? France and Britain. So most of the answers to questions about text is named entities. So when you do the named entity recognition, you are providing a very good input to this question answering system. And usually the relationships exist between these names. For example, France and Britain, so they are forming a group and that kind of stuff. Okay, so before doing anything further, many times natural language applications perform named entity recognition. That's what we are going to do. We are going to take a sentence. Foreign Ministry spokesman Shen Gaofang told Reuters that, okay, we are going to say this organization, this is other, person, other, organization, other, okay. So I am going to classify each word as a named entity or other. If it's a named entity, I am going to say the type of it. Okay, and it's not an easy application. Why it is not easy? It is not easy because the boundaries are kind of so blurred. Okay, give an example, or maybe I should take 10 minutes of break. After the break, we will continue. Okay, are there any questions? I can take a question about the name that recognition. Okay, after we come back, 14:33. Okay, I will take your questions. Okay, see you in 10 minutes. Okay, everybody. So the named entity recognition is hard because we don't know the boundary of the words. For example, I mean, is it First National Bank is the organization name, or the National Bank is the organization name? We don't know. First National Bank denotes to donate to Vans to Future School of Fort Smith. Okay, so I mean, National Bank or First National Bank. Also, the Future School or the School of Fort Smith. We don't know. Hard to know where it starts, and hard to know is it the part. For example, this Charles Schwab is the person who founded an organization, and the name of the organization is Charles Schwab. Is that person or is it an organization? So it's a hard problem. So how we can solve this problem using the neural network is going to be our toy problem. We are not going to solve the whole thing, but we are going to use it as an example problem of NLP. So the idea is this. Of course, we are not going to give a single word and ask for the classification. We need to give the whole sentence or a number of words. Okay, and then we are gonna get this person, location, organization thing. Okay, this is the idea. Okay, we will try to let's say our problem is simpler. Okay, we are going to do something simple. For a given word, we like to say if it's a location or not. Okay, we are going to classify if a given word is a location or not. So in this case, given these 5 words, museums in Paris are amazing. Is Paris a location or not? That's the idea. This one is going to produce location or other, L or O. Okay, L or O. So for this, that's what we are going to do. We will put Paris in the middle. Okay, and we will put the museums in are and amazing around it, and we will make a vector out of it. Let's say each word has 4 element vectors. 4 is a very small number, but for the sake of educational purposes, let's say each word has a 4-dimensional vector. Okay, and if I put them together, that makes a 20-dimensional vector, right? So X window is a 20-dimensional vector. So formula is 5 times D. If D is 4, 5 times D is 20. So my input to the whole system is going to be 20. Okay, 20 elements in it. So previously I have obtained my vectors from word2vec or some other place. Okay, good. I could have done this using the softmax approach that I have introduced before, but I don't want to do that because softmax can do only linear classifications, and this one requires more power than linear classifications. Okay, so this is the simplest window classifier softmax. This is what would have done. Okay, if you are doing this with softmax, how many parameters do I need? How many weights do I need in my softmax classifier? Okay, let me go back to here. As I said before, I have R20 inputs are X's are R20. Okay, 20-dimensional vectors. Okay, if nobody else answers me, I will ask Salman. Anybody? How many parameters do I need if I am using a softmax classifier? How many numbers do I need to find out?
101.
101. So, Kıvanç, you are giving me a number and you are not saying anything. How did you figure this out?
There are 5 inputs. Every one of them have 20 dimensions and 1 bias.
What? Say that again. I did not get the beginning part.
5 inputs, and every one of them has 20 dimensions.
No.
And plus,
Everyone has 4 dimension.
o zaman 21.
In that case, so 20. Well, remember, this is not neural network. This is a softmax classifier. We don't have the bias here. How many classes do we have? How many classes do we have? Anybody?
Two classes, location or other.
Yeah, so I have 2 classes, right? C is 2. So from 1 to 2, I need to have 1 vector for each C, and each vector has to be multiplied, with this x. X is 20 dimensional. So that means that I need 2 weight vectors. That means 2 times 20 is from the weight vector. So I need total of 40. 40 numbers. Once I figure that for those 40 numbers, then I can do this with a softmax. But softmax, as I said, it can draw only a line, and lines are not that useful for me. For me. Okay, so I will switch back to multi-layer perceptron, okay, or neural network. Okay, I will introduce an additional layer in our softmax classifier for nonlinearity, and we want to classify whether the center word is a location. Okay, so this is what we are going to do. This is our 20-dimensional input, and I will put that into many many sigmoid functions like this. Okay, w x plus b, and I will put it through this f. Okay, and I will have 8 of them. See, there are 8 neurons. There are 8 A's. There are 8 of them. Then after that, at the final layer, okay, I have a score layer here. Score is calculated like A times UT. U is the weights for this final layer. Okay. So my input is 20-dimensional, like this. My input is 20-dimensional. What is the size of my W? W is, okay, since I have 8 neurons, and each neuron will have 20 elements, 20 weights in it. So W is going to be R8 times 20. Of course, for each neuron, I will have a bias. So there will be a size of 8 bias vector. And in my case, U is going to be, if I am doing the softmax, of course, with the softmax, I have 2 classes. And 8 is going to be my input to the softmax this time. So 8 times 2 is going to be my softmax weights. Okay. This is what I am going to see, a neural network feed-forward computation. Okay, I put my stuff in here. I multiply each x with w's, and I add b to them, and I feed them through the sigmoid, and it will produce me 8 numbers, and I will put those 8 numbers into this softmax function, or the score function if you like to call it that way. Okay, so this is our softmax, this is our multi-layer perceptron, just as added a single layer. So we have the nonlinearity defined in them. Okay, so the middle layer learns nonlinear interaction between the input. So middle layer kind of, since each one knows about each term, okay, each one is trying to detect something, and at the end they kind of interact with each other. Okay, good. So I think I did, if I go to this example, regenerate. Okay, good. So I added, if my input is size 2, just 2 inputs, and in the middle layer I have 5 neurons, not 8. And if I try to find a classifier for this case, very interesting. In the middle all blues, outside is surrounded by the oranges. Find it. It's trying to find something. It's still linear. Okay, I think it's going to find it. Okay, this is standard gradient descent algorithm running here, and I think it is going to do a good job. Yeah, loss is very, very small, 0.05 maybe, and I don't think that it can do better than that, because those oranges near the center, so these cannot be classified correctly. If you try to classify them correctly, then you need to get some blues in them. That's not going to be good. So by adding this non-linearity, I can have this kind of a behavior, and I like to do the same thing with the NER, named entity recognition problem. Okay, so good. So feed forward means that put your input in here and get the results at the end, 1 or 0. We call them feed forward networks, and it works like this. You get your input, multiply it with this weight, add b's, and get z. Put your z in your f sigmoid function, get a's, and multiply the a's with this weight vector, and you will get s. Okay, so your scores. Okay, so, and these will be our parameters. This is a parameter, this is a parameter, and this is a parameter. Question: is a parameter? Is a and z are parameters? Are a and z parameters? I am not hearing anybody. Okay, Murat, you tell me. Murat Beyaz. Murat, are you there? Okay, good.
Yeah, I'm here.
Murat, is a parameter?
I guess it is because we can define the numbers of layers and neurons in our model.
Well, yeah. Maybe you are right. If you think like designing the system is your task to do, but your system is fixed. I gave you this already, okay? This system is fixed, and you are not going to change the number of neurons, okay?
Then, in my opinion, it's not a parameter because I cannot change.
Yeah, because you don't change, right? It is fixed. X is the simple system input. W and B and U are the system parameters to optimize. A and Z are automatically calculated from the input and the system parameters. A and Z are not system parameters. I mean, our optimization will not make a decision on A and Z. Okay, so given the system parameters and the input, you put your X, you multiply it with W, add it through the sigmoid and through this matrix multiplication, and you get your results. This is the feed-forward neural network computation. Okay? Okay, good. Any questions? Let me continue with the how we can do this optimization. Okay. I think this is what we were doing. Okay. This is what we were doing. Input is 20-dimensional. The sigmoid there, and this multiplication will give us remember previously we said that we are doing softmax. Here in this case we are not doing softmax. It's just a simple vector multiplication, okay, and then we get the result and we put it in a sigmoid to get a number between 0 and 1. So this is going to give a score, okay, just a score. And that score, if it is closer to 1, that means that the center word is a location. If it is closer to 0, then that means that that word is not a location. Very simple multi-layer network. Okay? A slight change. What is the change? Previously we had a softmax layer at the end. It was making a decision, two-class decision, true or false. This one is just gives a score between 0 and 1 for the scoreness of this given center word. Good. And we are going to do the stochastic gradient descent. What are we going to do? Once we write our loss, okay, once we write our loss, we are going to take the derivative of loss with respect to the parameters. And the parameters are this one, and that one. Okay. And we are going to change our parameters in a way that it decreases our loss. Okay. And we are trying to reach a loss of 0. Which is not going to happen, by the way. Loss of 0 is not achievable most of the time. Okay, so let's try to do this max the taking the gradient and trying to find the minimum stuff. Okay, so some reminders. Very nice. I got these slides from Manning, Christopher Manning. You know this guy. He's very good and his class notes are very good. I just borrowed it without his knowledge actually. Okay, so I am using them. So he included these nice slides about how to take the derivative of a function. You know this, right? If fx is x cubed, the derivative of it with respect to x is 3x squared. Okay, that's fine. Okay, so this sentence is important. You already know this. Okay. This one says that how much will the output change if we change the input a little bit, right? So if I change x just a little bit, okay, the rate of change of fx is 3x squared. It is very fast, right? 3x squared, it is very fast, okay? But if, let's say, if my function is like this, and if I take the derivative of df with respect to, okay, so what does that mean? If I change x a little bit, how much is the fx going to change? 0. It's not going to change anything, okay? It's not going to change, okay? It will, because it is constant. So this is important. That's why we say if I change theta a little bit, okay, but I don't have a single theta, I have hundreds of thetas, okay, how is the loss function change? Is it going to change a little bit or a lot or small? And in what direction am I going to change it? Okay, these are all given by this. So I need to be able to take the derivative of this kind of structure, okay? Of course, our derivatives will not be as simple as taking the derivative of a simple polynomial, because our functions do not have single dimensional inputs. Our inputs are going to be 100-dimensional, 1000-dimensional, okay? And other than the input, we are very dependent on the parameters, okay? And we are going to take the derivative of the parameters too. Gradients of a function with one output and n inputs, okay? Now we have a function that takes a vector as an input, like this. It takes a vector as an input. So how am I going to take the derivative? There is no single derivative like a scalar previously. It says that if you take the derivative of such a function of n inputs, your derivative will be a vector of size n again. So you are going to take the partial derivative with respect to x1, then x2 up to xn. So if your function it has one input, one output and n inputs, this is what's going to happen. So your derivative will be that. So what is the meaning of this one? What was the meaning of this thing? How much will the output change if we change the input a little bit? This is going to tell you how much the output changes if I change the x1 a little bit. Okay, that's the idea. How much the output is going to change. There is only one output. If I change the input x1 just a little bit, and all of them are there, okay? That's the meaning. So this is the gradient of a function with one output and n inputs. How about the functions that take n inputs and output m number of them? Okay, so a given function with m outputs and n inputs, m outputs and n inputs, it's going to be a function like that, okay? There are m functions in it, and each function takes n inputs. So by trying all the combinations, I need to take the derivative of f1 with respect to x2, x1, x2, x3 up to xn, and I need to take the derivative of f2 with respect to everything, and I need to take the derivative of fm with respect to everything, okay? And it's going to make a derivative matrix. We call this a Jacobian. It's the standard name for such matrices. And if you like to show it with this notation, the partial derivative of f with respect to x Then you put these indices, sub-indices ij here. Take the derivative of fi with respect to input xj. There are m functions and each of them has n inputs. Okay, good. So this is the Jacobian. So you already know about this, just a reminder. Chain rule, you already know this, I know. Okay, let's say if I have a function z that depends on y, and I have the y depends in turn on x. If I like to take the derivative of z with respect to x, what you're going to do, you take the derivative of z with respect to y times the derivative of y with respect to x. That's it. So this one with respect to y is 3. This one with respect to x is just 2x. So it is 3 times 2x, 6x. Okay. So if I have something like this, and we have many things like that, right? Or remember z is a n-dimensional vector. N is the number of neurons, and with this multiplication plus the addition, I get a z. So if I like to take the derivative of h with respect to x, what are you going to do? I am going to take the derivative of h with respect to z, then derivative of z with respect to x. Okay. So what is this? This is f prime z times w, right? W is derivative of z with respect to x. And if you take the derivative of, okay, how do you take the derivative of fz? dc, okay, it will be derivative of times 1. This f prime z came from there. Okay, good. So chain rule, we know that. So we are going to use these. We are going to use these rules to do our optimization stuff. Okay, so I think it's going to continue with what I did. Okay, good. So I just did it with the shortcut way. It is giving me this one. It is taking the derivative of h with respect to z, but z has many elements in it. So if you take the derivative of such a thing, what you get is the Jacobian matrices derivative, and that's going to be just a diagonal of the whole matrix. Since all the other values are going to be 0, because you are taking the derivative of zi with respect to zj, which is 0. They are not dependent on each other. I will put zeros in the upper part and the lower part. Only the diagonals will be non-zero. And this is what you get, element-wise activation function of the sigmoid that we have used. Okay, other Jacobians. Did you understand this one? Did you understand this one? Say yes. It's not difficult. Is anybody going to say yes? Okay, Mustafa Cemil Güney.
Yes.
Okay, thank you, Mustafa. Okay, how about this one? This is identity. Why? Because I am not saying one, right? Why don't I say one? Why don't I say one? Nida, you tell me, why don't I say one instead I say identity?
I'm not sure.
B can be anything other than 1. And it's diagonal.
B can be what again, Kıvanç?
B can be other than 1 if it was all 1, but it wasn't.
Well, identity is something like this, right?
Yes.
So I am not saying it is not 1. I mean, if you take the derivative of this part, it is 0. And if you take the derivative of B with respect to B is 1, right? But I don't say 1. I say identity. Why? It's because B is not a scalar, it is a vector, and I have a vector addition here. Okay? So we say it is identity matrix. So we looked at just 3 examples using the techniques that we have learned. Okay? So we said that if you take the derivative of fz with respect to z, it's going to be the thing that I wrote here. Okay, fz times w. If you assume that z is a scalar number, but if you assume that z is a vector, then it's going to be just the diagonal of the Jacobian. Okay, diagonal of the Jacobian. So we learned 3 stuff, and we are going to use this later. And this one is kind of obvious, right? So if you take the derivative of this with respect to u, that's what's going to take. u's go away, and I have this h. Just let's ignore this t for a while, I mean the transpose, because we are going to use transpose notation the way that is good for us. So it's not going to be strictly the transpose notation that you know from matrix algebra. Okay. So let's go back to the our neural network again. So if I like to do this, if I like to take the derivative of s, the score, okay, with respect to b, not with respect to u or with respect to something else, with respect to b. As you see, I don't see any b's in here, but this h depends on b. So what am I trying to find here? Okay, read this in English. Remember the sentence that I underlined at like 10 minutes ago? Using that sentence type explanation, explain this to me. Okay, first let me ask this question. What is score? What is S? Somebody tell me what S is. What is S?
U transpose times hash.
Yeah, that's yeah, that's the formula, but no. What is the explanation for S?
Output class.
Our output, but why do we call this output? Why? I mean, tell me the possible values for that S. What does S represent? What does it give me?
A scalar maybe. Class.
A scalar, but what kind of class is that? This is our problem, right? What are we trying to do? We are trying to do this named entity recognition thing, right? So S is going to be a score for this word, this Paris world, to be a location. If S is if S is high, then this center word is a location. If S is low, then this center word is not going to be a location. So let's try to read this one. What does this mean? Derivative of S with respect to B. What does that mean? Read that formula in English. S is going to give me the score. It will say that, okay, if this number is high, then X Paris, I think that X Paris is going to be a location, okay. If this number is low, then it's not a location, it's something else. I already interpreted this formula, but how about this one? How about this one?
How much the output change bias?
Okay, two people started with how much, and that's I like, okay, but I did not get the rest. How much again?
How much the output will change if I change bias?
Yeah. How much the output score changes when I change the bias. Okay. So if I am increasing the bias, if score is going high, then I will do it, right? I will keep increasing it. If I am lowering it, then score is going to low, then I am not going to do it, right? But the problem here is that B is not a scalar, just single scalar, because there are how many B's? There are 8 B's in here, right? So there is no such thing as just increasing B or decreasing B. There are many different directions that you can take. Okay. So this is a nice question. What happens if I change the vector B a little bit? What happens to S? And by taking the gradient, it's going to give me that information. Also, it's going to give me the steepest direction where I can change this B. Okay, it will tell me that, okay, this is your direction, 8-dimensional direction. If you walk in this 8-dimensional direction, your S will increase. That's good. Okay, so that's what we're trying to find now. So let's take derivative of S with respect to B, but S depends on H and H depends on B. That's what I'm going to do. Okay, so S is this, okay, H is this one, so I know everything here. Okay, so S depends on H depends on Z, and Z depends on B. Okay, so let's take, what is this? Can somebody tell me what this is? Partial derivative of S with respect to H. I think we did this before. We definitely did this before. What is this derivative? Partial derivative?
U transpose?
Yes, exactly. UT, okay. We did that and we get UT, and we are going to do that, and we are going to do that. Okay, so In fact, we did all of them before, okay? This one, okay. Okay. And this one and that one. So this one is U transpose, as we said before. How about this one? H with respect to Z. Okay. H with respect to Z. I think it is this one. It is diagonal of all the F functions, derivative of all F functions. So that's it. So ut is a vector. This one is going to be a what? This one is going to be a matrix, but only the diagonals are there. Okay. And then partial derivative of Z with respect to B is going to be identity. So I put an identity in here. Okay. So I found it, right? I found the derivative of S with respect to B. Okay. And since I know my F function, what is my F function? F function is Fc, remember this one, 1 over 1 plus e to the minus z. I can take these derivatives, right? And I put all those z's in it. I try to find u's already. Okay, I try to find those parameters u's already. So those are the parameters. So that's something. That's something. It shows that I am making progress. Okay, so if I am changing the b's a little bit, what happens to s's? It depends on the u's. Also, it depends on this sigmoid stuff. Okay, good. So this is element-wise multiplication. This is not dot product. Okay, this is element-wise multiplication. So I am going to take the diagonals of this Jacobian matrix, which is the derivatives of all the derivatives of all the f functions evaluated at z. I am going to multiply them by u. Okay, element wise. I will ignore this one because it is identity. Okay, I like to do the same thing with this one now. Okay, previously I did this. Okay, previously I did with respect to bias. If I change the bias a little bit, what happens to S? Now I am wondering, if I change the weights of the first layer, what happens to S? Okay, the formula is here. Okay, remember the previously this part. Okay, maybe okay. So if I do this and do this, I see that this part will be the same, exactly the same. So I don't have to calculate that part. So if I keep them somewhere, I can use this trick to make less number of calculations. Okay, so we have to be smart in that case. Sometimes some people call this a delta. Okay, they say that at this layer, when you are taking these derivatives, okay, what you are doing is you get this, okay, you multiply it with this one. In this case, remember, this green one was identity, but this black one is not going to be identity, it's something different. So this delta is going to be the same. So how about this? Delta, the derivative of S with respect to W with matrix. This is a matrix, right? And one output, nm inputs, 1 by nm Jacobian. So, I mean, all we are trying to do is this, remember this theta has W's in it, W1, W2, W3. Also, it has the biases in it. Okay. But if I treat W like a matrix, then this idea will not work. So from time to time, I will treat my W as a matrix, and other times I will treat it as part of this very long one-dimensional vector. Because at the end, I like to be able to calculate this one for each iteration of my gradient descent. Okay. So I need to reshape it from time to time. That's why we call it reshape convention, and I'm not going to go into details of that one. Okay, and the transposes are used for that kind of stuff. So it looks like I told you how the derivatives work, how we can take the derivatives of your score, your final output with respect to your parameters. Okay, basically what we are doing is we are taking the chain, we are using the chain rule from the output of your network back to the parameters, and we are finding formulas for what happens if I change this parameter a little bit, what would happen to the final output, and we are changing our parameters accordingly. Okay, so now we have enough stuff in our hand, powerful enough stuff in our hand to do the back propagation, to do the training, okay, to find the real stuff. Let's look at them. Okay, are there any questions? Are there any questions? So it looks like it is time for a break. Let's take 10 minutes of break. 15:35. We will be back at 15:35. Okay, so let's look at the idea of backpropagation. Can you tell me the biggest difference between backpropagation and forward iteration of a neural network? What is the biggest difference between backpropagation and the forward iteration?
Backwards is only needed when we need a gradient.
We need a gradient. Well, yeah, of course, without calculating the gradients, backpropagation is not applicable at all. But why do we need backpropagation?
To learn?
Yeah, that's what I'm trying to say. Backpropagation is for training only, okay? When you are doing backpropagation, you are doing it on the gradient of the loss function, okay? When you are doing the forward iteration, you are using your neural network, okay? You are using neural network. There is no training with the there's no training when you do the forward iteration. Okay, usually we show our networks like this. Okay, this is called computation graph. Okay, remember this was our neural network for the named entity recognition problem. So I take the X, I multiply it with this matrix W. This was the neural network parameters, and I add the results with this vector B bias vector, and I feed it through this F. Okay, F is the sigmoid function. Of course, there are many elements of this vector at the end, and this function is applied to each of element of these, and this will result another vector. I will dot product that vector with this U. This is another parameter, and as a result of this, I will get a score. Okay, so the source nodes, okay, are inputs. This is the source. These are the input. Interior nodes are the operations. Dot product plus f function dot product again. So this is a graph actually. This is a graph. Okay, and we are going to show the backpropagation and forward iteration on this graph. Okay, and each of the edges show the results. Okay, so this edge represents the result of multiplication of these two. This edge shows the addition of these two, etc. So the data flows on the edges. Nodes show the calculations. So forward propagation, forward iteration, we know how to do it. We just follow these paths. So this is for calculating our score given the input and the given the input and the system parameters. I would calculate the score for the input. Okay, so let's try to do the backpropagation. By doing this, let's try to calculate this one. Okay, derivative of score with respect to B. If I change a little bit of B, what happens to the score? So I start from here, derivative of score to score, but score depends on H. Okay, and I take the derivative of S with respect to H, with the chain rule, I have to take the derivative of S with the Z and S with the B. So we need to calculate it. So how do I calculate it? Using the chain rule. And with this graph representation, this is what I have. This black stuff is the forward propagation, forward iteration. Z comes in, I feed that Z into F, function F, and I get H.